In this lesson, we will learn about a type of series called a power series. So here is the definition of a power series. Suppose x is a variable, then an infinite series of the form, sum from n equals 0 to infinity of some coefficients a sub n multiplied by x to the n power is called a power series. Specifically, this first one is a power series centered at c equals 0. Now, a series that is centered at some value c is of the form a0 plus a1 times x minus c plus a2 times x minus c squared, etc. So we have infinite sums of coefficients and then variables to powers. And you've already seen some of this already, at least approximations of it. In the last lesson we said something like e to the x was about equal to 1 plus x, or a better approximation was 1 plus x squared over 2 factorial. An even better approximation was 1 plus x squared over 2 factorial plus x cubed over 3 factorial. We talked about how to find these Taylor polynomials. Now in general, you could actually prove that e to the x is equal to, not approximated by, but actually equal to 1 plus x squared over 2 factorial plus up to xn over n factorial, etc. So the infinite sum from n equals 0 to infinity, x to the n over n factorial. We'll talk about how to find stuff like that in the later section. So the first example is to state where the following power series are centered. Now this first one, since we just have x to the n, this is centered at c equals 0. The second one, we have x minus 4. This is centered at c equals 4. And the final one, we have x plus 5 to the n. Well, x plus 5 is the same thing as x minus negative 5. So this center is at c equals negative 5. Now, a power series in x can be used as a function of x, where f of x is equal to the sum from 0 to infinity a sub n x minus c to the n, and the domain of f is all x for which the power series converges. And every power series converges when x equals c. When given a power series, there are only 3 possibilities. The first one is that the series only converges when x is equal to c. The second one could be that the series converges for every x. And the third one says that there is a positive number r such that the series will converge if the distance between x and c is less than r, and diverges if distance between x minus c is greater than r. The number r in the third case is called the radius of convergence of the power series. In the first case, if x equals c, you say that the radius of convergence is equal to 0. In the second case, if you converge for all x, you say that r is equal to infinity. And what this means in the third case, if x minus c is less than r, it means that if you have, say, values that are either r above c or r below c, those are going to be all the values for which this power series will converge. It's kind of a one-dimensional circle in some sense. All the points that are plus or minus r from c. Let's find the radius of convergence for this particular series. So if we let a sub n equal the terms in this series, so x minus 3 to the n over n, we can apply the ratio test. So find the limit as n goes to infinity of an plus 1 over an. We know that the resulting series will converge if the value of this limit is less than 1. So plug everything in. The limit as n goes to infinity, so an plus 1 will be x minus 3 to the n plus 1 over n plus 1, then multiplied by n over x minus 3 to the n. Now let's simplify a little bit. So x minus 3 to the n plus first is the same thing as x minus 3 to the n multiplied by x minus 3 over n times x plus 1 multiplied by x minus 3 to the n. And now the x minus 3 to the n's cancel, and we have the limit as n goes to infinity, absolute value x minus 3 multiplied by n over n plus 1. And technically, x minus 3 is a constant, so you can factor that out of the limit. And the limit as n goes to infinity of n over n plus 1 will equal 1. So the value of this limit is equal to x minus 3. And we know that this will converge if this absolute value of x minus 3 is less than 1. And this final conclusion tells us that the radius of convergence r is equal to 1. Next, let's determine the radius of convergence for this series. So once again, we'll let a sub n equal x minus 2 to the n over 5 to the n. Now, you can apply the ratio test. You could also apply the root test. Let's do that. So let's do the root test. So we have the limit as n goes to infinity, the nth root of the absolute value of a sub n. So we'll take the limit as n goes to infinity of the nth root of x minus 2 over 5 to the n, all absolute valued, which gives us the limit as n goes to infinity of absolute value x minus 2 over 5. And since there's no n's left, this is just a constant, so my limit is x minus 2 absolute valued over 5, and we will this series will converge if this is less than 1, and that implies that the absolute value of x minus 2 has to be less than 5. And this final inequality tells us that our radius of convergence r is equal to 5. One could have also used the ratio test to come to the same conclusion that we have right here. Next, find the radius of convergence of n factorial times x to the n. So once again, we'll let a sub n equal n factorial times x to the n, and we'll use the ratio test. So find the limit as n goes to infinity of a sub n plus 1 over a sub n. So that will be n plus 1 factorial multiplied by x to the n plus 1 over n factorial multiplied by x to the n. Alright, so n plus 1 factorial is the same thing as n plus 1 multiplied by n factorial. X to the n plus 1 is the same thing as x to the n times x, all over n factorial times x to the n. So the n factorials cancel, the x to the n's cancel, and we're left with the limit as n goes to infinity of n plus 1 multiplied by the absolute value of x. And this will be infinite as long as x is not equal to 0. So this converges only at x equals 0. So only at that one point, which means that my radius of convergence r is 0. Let's find the radius of convergence of this rather semi-complicated looking series. So once again, we're going to use the ratio test. So we'll find the limit as n goes to infinity of a n plus 1 over a n. And I'm letting a sub n equal the terms of the series, negative 1 to the n, x to the 2n over 2 to the 2n, n factorial squared. So first, just very carefully input n plus 1. So we'll have negative 1 to the n plus 1 x to the 2 times n plus 1 over 2 to the 2 times n plus 1, and then n plus 1 factorial squared, and then multiplied by 2 to the 2n, n factorial squared, negative 1 to the n, x to the 2n. So first of all, the negative ones they're not going to affect the convergence or divergence here, so I'm just going to drop them. You could say we absolute valued them and they became 1. So what we have now is the limit as n goes to infinity. So first, this x to the 2n plus x to the power of 2 times n plus 1. That will be x to the 2n plus 2. So that would be x to the 2n times x squared. And then from the other second fraction, we have 2 to the 2n, and then n factorial multiplied by n factorial. Now, with this expression, we'll have 2 to the second times, or 2 to the 2n, excuse me, times 2 to the second. Now, n plus 1 factorial is the same, squared is the same thing as n plus 1 times n factorial, and then another one, n plus 1, n factorial. And then finally I have the x to the 2n. And a whole bunch of stuff should cancel. So the x to the 2n's cancel, the x squared stays, the 2 to the 2n's cancel, the n factorials cancel, so all I have left in the numerator is x squared, and the denominator I have 2 squared, or 4, multiplied by, it appears to be, n plus 1 squared. So this is equal to, we can factor out that x squared times the limit as n goes to infinity of 1 over 4 times n plus 1, the quantity squared. That limit is 0. X squared times 0 will equal 0 always, no matter what x is, which is less than 1. And so this series will converge for any x, and thus we have that the radius of convergence r is infinite. Now, the final thing we're going to check, this radius of convergence told us, for example, that if you were plus or minus a certain value from your center, you're going to converge, but it doesn't tell you anything about the endpoints. So let's do an example where we also test the. So find the interval of convergence for this power series. So once again, we'll let a sub n equal negative 1 to the n, x minus 1 to the n over n plus 1. So find the limit as n goes to infinity of a n plus 1 over a sub n. So we'll have negative 1 to the n plus first, x minus 1 to the n plus first, over n plus 1 multiplied by n plus 1 over negative 1 to the n, x minus 1 to the n. So the negative ones really don't matter. We can absolute value them and make them 1. And we'll have x minus 1 to the n multiplied by x minus 1, and then n plus 1. In the denominator we have n plus 2 multiplied by x minus 1 to the n. And the x minus 1 to the n's cancel, leaving us with absolute value x minus 1 multiplied by the limit as n goes to infinity of n plus 1 over n plus 2. That limit is 1, so this expression is equal to the absolute value of x minus 1. And by the ratio test, this converges if this expression is less than 1. And now what that will imply is that x minus 1 is in between negative 1 and 1, or x is in between 0 and 2. Now we need to test at x equals 0 and at x equals 2 to see if this series will converge or diverge. And this is because when the value of the ratio test is equal to 1, you have that you cannot make any conclusions about the convergence or divergence of the series. So at x equals 0, if I input 0 into the series for the x, I get the sum from n equals 0 to infinity, -1 to the n, -1 to the n, all over n plus 1, which is the sum from n equals 0 to infinity of just 1 over n plus 1. And you could use probably the limit comparison test to show that this diverges. So just tell me what you would use. So diverges limit comp. So that one diverges. When you plug in x equals 2, the series becomes the sum from n equals 0 to infinity, -1 to the n. 2 minus 1 will be 1. 1 to the n is just 1 over n plus 1. And this will converge by the alternating series test, or the AST. So that tells us that the interval of convergence of this series is that this series will converge as long as you have x is greater than 0, but less than or equal to 2. Another way to write that would be parenthesis at 0, closed bracket at 2. Find the interval of convergence of this series. So once again, begin by applying the ratio test. Find the limit as n goes to infinity. So first input n plus 1, x to the 3 times n plus 1 over 3 times n plus 1 factorial, multiplied by 3n plus 1 factorial over x to the 3n plus 1. So that's the limit as n goes to infinity. So we have x to the 3n plus 4 multiplied by 3n plus 1 factorial all over 3n plus 4 factorial x to the 3n plus 1. Now you can think about x to the 3n plus 4 as x to the 3n times x to the 4th. It is 3n plus 1 factorial. Now 3n plus 4 factorial would start with 3n plus 4. 1 down would be 3n plus 3. Then 3n plus 2, and then it's 3n plus 1 on. So 3n plus 1 factorial, x to the 3n times x. And you can see that the x to the 3n's cancel, the 3n plus 1 factorials cancel, and this x will cancel with one of those x's, giving us the limit as n goes to infinity, absolute value x cubed over 3n plus 4 times 3n plus 3 times 3n plus 2. And this limit will equal 0, which is less than 1 for any x. So in this case, we have that the radius of convergence r is infinity, and the interval of convergence, which I'm going to just call the IOC, is minus infinity to infinity. So this converges for all x. Find the interval of convergence for this series. So once again, let's apply the ratio test. So find the limit as n goes to infinity. So first, let's input n plus 1. We'll have n plus 1 factorial, x plus 1 to the n plus 1, all over 1 times 3 times 5, up to 2n minus 1, and then plugging in n plus 1, 2 times n plus 1 minus 1. Then multiplied by 1 times 3 times 5. That's sometimes called a double factorial, the product of all the odd terms. N factorial, x plus 1 to the n. So obviously all this junk will cancel with all that stuff. So limit n goes to infinity, we have n plus 1 multiplied by n factorial, x plus 1 to the n multiplied by an x plus 1, all over, this looks like a 2n plus 1, an n factorial, and an x plus 1 to the n. And a whole bunch of stuff is going to cancel, so the n factorials cancel, the x plus 1s to the n cancel, and we have the limit as n goes to infinity, absolute value x plus 1 multiplied by n plus 1 over 2n plus 1. And the limit of this stuff is equal to a half, so we'll have finally x plus 1, half of that must be less than 1, which tells us that the absolute value of x plus 1 must be less than 2. So the radius of convergence, r, is equal to 2. Now translating this into an interval, we'll say that x plus 1 must be between -2 and 2, which implies that x is in between -3 and 1. Next, we have to test our endpoints. Now, when you plug in x equals -3, we have the sum from n equals 1 to infinity of n factorial times -2 to the n over 1 times 3 times 5 up to 2n minus 1. And when you plug in x equals 1, we have the sum from n equals 1 to infinity of n factorial times 2 to the n over 1 times 3 times 5 up to 2n minus 1. Now, these both appear to diverge, but I'm afraid that I don't have a great explanation for you that is calculus 2 appropriate. Both of the explanations that I've come up with have been pretty complicated. So I'm going to have to either come back to this or just know that on a homework or test question, the divergence or convergence of the endpoints should be a little bit more obvious. So in this case, my interval of convergence is -3 to 1, which you could also write as -3 is less than x, which is less than 1.